I am so sorry for the torture I put you through in those really long videos. I think they were necessary, sorry. And I'm also really sorry for the quality. We now have a decent microphone and a decent camera, so this will be a lot better. All right. So now we are making a major transition in our class. We are moving from inductive styles of reasoning to deductive styles of reasoning. Please note that it is very normal in this class that if we tried to cover all the material, we would go way too fast and technically it would take longer than a semester. So we're skipping over the diagnostic explanation material and going straight to the deductive reasoning section of the class. Oh, and please notice, I'm going to get technologically savvy here. We have to do this. I really need a board to teach with, so instead I'm going to create a visual chalkboard right here, and I'll be making notes with it. Should I pretend like I'm actually writing and doing things? Yay. All right. So let's begin by first making a little step-by-step chart. We'll review how we handled induction, and then we will transition to how we handle deduction. So the first question when you're faced with an argument is the trickiest one, but again, this is not something I will be testing you on. It's not important for being an intelligent person in the everyday world. But so question one is always, are we handling a deductive style of argument or a deductive style of argument? So first question, inductive or deductive? And then once you find that, right, then we have different styles of how we assess the quality of the argument. Really briefly, if it's an inductive argument, then you have a four-step method basically. You first ask step one, are the premises relevant? Step two, are the premises truthful? And we know that if a premise isn't at least a little relevant and at least a little truthful at the same time, then it does not help your argument. Step three, sufficiency. Is there enough evidence for that conclusion? And then finally, we judge the strength. And remember, inductive arguments are all about likelihood, so we judge how likely is this conclusion based on the evidence provided. Done. Now we talk about the steps for judging deduction. So if we find that our argument is deductive, our next question is it valid? This will be the biggest question. This is what we will spend almost all of our time on for the rest of the semester, testing the validity of arguments, right? So first, let's just fill in the chart, and then we'll go into more detail about what it means to be a valid argument. Deductive arguments are formal, and so their analysis is also formal. There is none of this kind of loose judgment about how likely or how relevant or if it's somewhat true. In deduction, these things are absolute yes or no questions. So, if it's deductive, ask if it's valid. If it's not, the argument is invalid and you stop, the argument completely fails. Done. But if the argument is valid, then you go to the next question. Is it sound? And if the argument is not sound, you would write unsound and you stop. The argument again fails. So we could lose a deductive argument. If it's invalid, we stop. If it's valid but not sound, if it's unsound, we stop. But if it is both valid and sound, then we reach the final step and it is a perfect argument. It is a proof. It is a certainty. So if you pass through all the levels, it is valid, it's sound, then it's a proof. We have a certainty argument, and this is actually what proof means. Many people use the word proof very loosely, but a proof means that the conclusion is absolutely certain, it is perfectly logical, and absolutely true. All right. So now let's talk briefly about soundness. We will come back to validity. That is the bulk of what we need to learn. That is the tricky part. So let's talk about soundness. Soundness is a very simple sort of question. When you're asking if an argument is sound, remember, it has to be valid first or you don't even ask if it's sound. Soundness simply means that the premises are actually true. In my history of teaching deduction, I find that the class separates itself into, let's say, 4 groups. There will be a small percentage of you, right, say 10% of you, who will find this not only easy, but fun. You will, and trust me, it would annoy you normal people. There will be some of you nerds that will want this to be harder, will want me to give you harder examples because you find this just like a puzzle solving video game. You will think this is great fun. And by the way, I do too. I think this is so fun. It is a problem solving game. Now, second group is a large group. The second group is about 50% of the class that you find this stuff easy. You will find yourself getting really high scores. Maybe you'll make some tiny mistakes on tricky examples, but by and large, you'll be very confident, and so you'll like this material. Now, so we have 40% of the class left in the next two groups. And I find they divide themselves fairly evenly. So there will be about 20% of you who will find this material scary. But you will trust me, you will follow the steps, and here's what will happen. At each level of the learning curve, you will feel, I don't think I'm getting this. This is really difficult. I'm going to follow the steps, but I'm sure I'm doing this all wrong. And then you will find that, oh my gosh, I can't believe it. I'm doing it right. You will not have confidence, but you will trust me, and you will see you will do well. Maybe you'll make some mistakes here and there because you do get nervous on a problem, but you will do very well. And in fact, the unnerving part about it is that you will find that as you're trying exercises, oh no, I'm not sure I'm getting it. But by the time the big quiz comes around, you will do fine. And you will be shocked how well your scores are. That brings me to the last 20% group. That is the group that does find this fairly scary, right? They will follow the steps, and their success will depend on trusting the steps. If you do trust me, you will get this. Now, in those last two groups, let me say a little bit more about the experience. You might not feel confident in your ability to deal with the theory. And so notice, those are two different things. I hope that you fully grasp how this works and its importance and what it means about intelligence. But sometimes you won't grasp the theory. You won't see how this works, or more importantly, why it works. But again, you will still be able to succeed at the skill. So this would be like, say, a certain cooking skill or working on a car in a certain way. It would be best if you fully understand how the recipe works, how that car part works, but you still can follow the steps, follow the recipe, follow the instructions, and get it right. So please, right, if the theory is still baffling you, don't worry too much. You can still do well at this skill. So now we're ready for the first real difficult part of the theory. Again, please try your best to understand the theory. It'll make you much more comfortable with the point of all of this, but don't stress yourself out. You can still do well if you don't understand the theory right away, or even if you don't understand it fully at the end. You can still do very well at this skill, even if you don't feel confident about the theory. But let's try it. So we are right now at the step of talking about validity. We will review soundness a little bit, but again, you'll see that's very straightforward. So now we're focused on validity. So what does it mean that an argument is valid? Let me first start by talking about the word in its just ordinary sense. So when we say that something is valid, or someone makes a point and we say, oh, that's a valid point, please know that a lot of times people aren't understanding clearly what they mean. Valid does not mean that the point is true. If we say a person's argument is valid, we're not saying the argument is true. Notice, that's not actually what the word valid means. In its most everyday sense, the word valid means something like consistent or logical, right? Or it makes sense. So when I say that someone's point is valid or their argument is valid, I am saying that given your assumptions or given your worldview or given what we're talking about, that point is logical and does make sense. I am not saying that I agree with it. I am not saying that it is true. I am simply saying that it makes sense or it's logical. Okay, so now let's turn to what valid means in logic. Valid is a term that only applies to deduction. And so what does it mean? So let me, now this, please don't be annoyed, but I'm going to give you a multiple layer definition here. I love the first early definitions. They actually capture its meaning. But then we will go to definitions that are the ones that if you look up what valid means and you're looking up its logical sense, you will find there the more technical definitions, but please note what those are doing. Those are the definitions we use when we're testing an argument to see if it's valid. But I think its meaning is best captured by these first two definitions. So these are the definitions I like the best, but we do need the other ones for when we come to test validity of an argument. The first and most basic definition is valid means the argument has perfect logical structure. To fill that out with more words, here is my favorite definition. An argument is valid if the conclusion follows necessarily from the premises. The key word there is necessarily. That means the logic has perfect structure, so where, and now here's where we get to the testing definitions, the definitions that you will find in textbooks. It means the conclusion follows necessarily from the premises, which means if the premises are true, the conclusion has to be true. Or look at our old definition. If the premises are true, then the conclusion cannot be false. Notice those mean the same thing. So notice, the key idea is the necessity of the structure of the argument. The conclusion follows necessarily from the premises, and if that's true, that means if. Notice, if means it's not automatically true. It means if we assume the premises are true, then with that assumption, the conclusion follows necessarily. So if the premises are true, the conclusion has to be. Notice that wording there. Has to be is important too, because that's what I meant by necessarily follows. If the premises are true, then the conclusion has to be true. Or, same thing, if the premises are true, then the conclusion cannot be. Again, a necessity issue. If the premises are true, then the conclusion cannot be false. That means we can now give a definition of invalid, but notice the language. If an argument is invalid, that means that if the premises, if all of them are true, it's still possible for the conclusion to be false. Notice, possible. The conclusion might happen to be true, but it's not necessary. Let me give a basic scenario, and let me use this example a few times, I hope. We can have a situation where the premises are true and the conclusion's true, but the logic is terrible. So let's try one right now, right? Premise 1. I am wearing a cream-colored or a light-colored shirt. Premise 2. I am sitting down. Therefore, I am your teacher. All those things were true, but did the logic make sense? No. We can easily imagine those premises being true and the conclusion being false. All I would have to do is put this shirt on my son, have him sit in this chair, and we would prove that the argument doesn't follow logically. Because what would we have, right? There is someone wearing a cream-colored shirt, there is someone sitting down, and does it necessarily follow that that person is your teacher? No. So we see that that argument does not follow, right? The conclusion, if those premises are true, for that argument, that conclusion can still be false. Why? Because there was no validity to the argument. The fact that I'm wearing a certain color shirt and sitting down doesn't necessarily lead to the conclusion that I am your teacher. All right, so let's summarize where we are so far. So let's look at an example and show how our method applies and also start getting used to the real goal here, which is putting into practice our judgment of validity. So let's take a basic example. Premise 1. If I am a husband, then I am married. Premise 2. I am a husband. What therefore follows? I am married. Now, this is step 1. Is it inductive or deductive? From now on, it'll be obvious all these arguments are deductive, so we can, from now on, skip this step. But this is a formal style argument. It is seeking proof. It is not an issue of likelihood. It is an axiomatic step-by-step process where all of the material needed for the conclusion is provided directly in the words and structure of the premises. All right, that's for the last time. Deduction, all of the arguments we will be looking at for this section of the class will hereby all be deductive arguments. Good? So, it is a deductive argument, so now we can apply our tests. So we ask, is it valid? Now notice the questions we ask. Is this perfectly structured? Does that conclusion follow necessarily from the premises? And, to use the technical test language, if those premises are true, does that conclusion have to be true? If those premises are true, can that conclusion have any possibility of being false? And the answer is no. Now notice, we haven't yet asked if they're actually true, but that conclusion does follow with necessity from those premises. The truthness of the conclusion follows if, keyword if, the premises are true. So in this case, this is a valid argument, so we can move to the last question, is it sound? And then we literally, again, this is very down to earth, this is not the difficult part. We read each of the premises and see if they're true. If I'm a husband, then I am married. Yes, that is the definition of husband. Premise 1 is true. I am a husband, right? You can look into it. It is true. I am a husband. My wife jumped on that grenade. You are welcome. She saved all the other women on the planet from being married to me. Yes, premise 2 is true. So what do we have? We have perfect logic. If the premises are true, the conclusion has to be true as well, and the premises are actually true. So notice, put those two steps together, and it results in the necessity of the conclusion being true. The conclusion follows logically, necessarily, and the premises are true. Therefore, it is a proof I am married. That is an absolute certainty. So now we are ready to learn how to test for an argument's validity. Our goals, this is going to sound weird, is first to look at the first three methods to get a good sense of how validity works, to get a good understanding of what it means for an argument to be valid, to get a good view at logical structure. That's what we'll use the first three methods for. But there is a second goal involved here. You will find these first three methods to be fairly frustrating. You will find that they work well for simple arguments with certain structures, but if you have a complex argument, imagine an argument with multiple premises, these will completely fail. They are not reliable methods. They are good for a general understanding of validity, so we should spend some time doing this quickly. But my second goal is to get you tired of them so you'll be motivated to learn the fourth method that actually works and works perfectly. The four methods are crude Venn diagrams, basic structure, imagining an invalid situation, and then finally, and we'll do this later, symbolic logic. In our case, we'll be using what's called SL, sentential logic. So first, let's just use our basic husband argument that we just talked about and show how we would test its validity. Again, just testing the step to see if it's logically perfect using our four methods. First, if we were to construct a Venn diagram, and we're going to do it in a very crude way, we are not going to be using the shading methods with three overlapping circles. We'll use a basic notion of sets. So here's what we do. We take each premise and put it in a set bubble so that we can see how it relates to the other claims in the argument. So premise 1 says, if I am a husband, then I am married. So first we need to have a bubble for I am married. So here will be the bubble of married, and here will be the bubble for husband. Now notice how we draw this. It says, if I am a husband, then I am in also the set of being married. So husbands is the smaller bubble inside the bubble of married. So now we are ready to draw onto our diagram so we can visually see the logic, the second premise. So there is the first premise. Now, second premise, I am a husband. So where do we put I? Where do we put Jeff? There he is in the husband bubble. So we have a visual representation of our two premises, and now we ask the question, does it necessarily follow from what the first two premises say that I am married? Look at it. Yes, that necessarily follows. So a Venn diagram works for a very simple argument like that, and it gives you a visual depiction of what validity is like. Try the second method. Second method is check the basic structure. Now, some people have a good eye for this, some people don't. Don't worry. This is partly why we'll use symbolic logic. We'll use a formal system, so it's not based on whether you're familiar with these structures. So let's first take our argument and lay out the premises in a basic structure. It says, if I am a husband, so we'll say, I am a husband, H. Then I am married. So we'll draw a little arrow. If you are a husband, then it follows from being a husband that you am married. Second premise simply says H. I am a husband. Now notice the structure. Does it logically follow that M must follow? That M can be concluded from the first two parts. And again, if you have a good vision, right, you have a good sense for these structures, you would see that that structure follows necessarily. That result, that conclusion M, is a natural result of the first two premises. Last technique. Third. Now, of course, we'll get to a fourth technique, which is the technique we'll be using, the one that you will be desperate for me to teach you, the one when you realize I'm going to be testing you on this, you are going to want to use SL and not the first three methods. But the third method, this one is very good. I think this is the best method for getting an intuitive sense of how validity works. So we will, in a way, mimic this when we teach sentential logic. The third technique is this. We try to imagine a situation where the premises are true and the conclusion is still false. Notice what we're doing. We're trying to see if this argument could be invalid by using our imagination. Remember, the definition of invalid is that it's possible for the premises to be true and the conclusion to still be false. So we're going to try that. So we read our premises and imagine they're true. So imagine we live in a world where if you're a husband, then you're married. That is our world, so it's easy to imagine, but we still have to imagine it whether it's true or not. Because again, we're testing logic, not truth. So imagine it's true that if you're a husband, then you're married. And then imagine that you, in this world you're imagining, are a husband. Can you imagine that world where you are not married? And we can't. We can't imagine those premises being true and you not being married, so this again logically follows. So this argument is valid. All right, so let's apply our three methods for testing validity to the examples on pages 9 and 10 of the syllabus. Be sure you have these out. Be sure to pause and work on this. Have a piece of paper out. I need you to try this. But don't lose track of our goals here. Our primary goal here is to give you a good sense of how validity works, to understand the meaning of it, and to see it applied to real case examples. The secondary goal, though, is the weird one. I'm trying to get you to see why we need a more precise method. Because what we will find is that using the first three methods, they only work on very simple arguments, and even then, when it comes to simple arguments, not all three of them work for every case. So you have to know all three methods very well to see which ones apply, and again, they only apply for simple cases and certain cases. So you will be begging me to teach you a more elaborate but more precise method. You do not want to use these methods on a big quiz. That would be incredibly unfair. But again, these are good at getting you an understanding of how validity works. All right, so we're only looking at the deductive arguments on pages 9 and 10. So let's start with example B. B is a case where two of our methods work. First, let's apply a Venn diagram. Okay. In a Venn diagram, again, right, we lay out visually the meaning of the first two premises in basic sets. So what would we have? First premise, those disgusting pigeons are in the family Columbidae. So what do we need? We need a larger circle for Columbidae, and then pigeons go inside that circle. Very clear, pigeons are in the set of Columbidae family. Premise 2, doves are in the family Columbidae. This is where I'm already getting pissed off, Because notice, we cannot assume anything but what is stated in the premises. So you can't even imagine you know what these words mean or whether they're true or false. You can only write down in your Venn diagram exactly what they directly state. So doves are in the family Columbidae. So where do we put them? Well, obviously they're inside the larger circle, but where in the larger circle? Could doves, now remember, we can only go by what's stated. In a deductive argument, the very words and structure is what you have to work with. You can't use your guess to fill in the blanks. The logic has to be perfect. So, where do doves go? Could doves technically be the same things as pigeons? Could they be a subset of pigeons? Could doves and pigeons sometimes be the same thing and sometimes not? Or are they completely separate? Again, we can't use our guess to fill in and say, no, doves and pigeons are separate, because it doesn't say that. So notice what kind of stupid thing we're going to have to do to use a Venn diagram. We're going to have to leave it open for what the relationship between the set of doves and the set of pigeons is. So we're going to have to say, we're not sure if they overlap, if they're the same, if they're different. We're going to have to reflect that in our drawing. Oh gosh, that's terrifying. Now, notice though, when we do lay out the image of the first two premises, does the conclusion follow? Yes, it does. Fortunately, the conclusion is not asking about the relationship between pigeons and doves. It's just saying, are they both in the family Columbidae? And clearly they are. So this argument, argument B, is valid. Structure. The structure method here doesn't work. We're not good at writing out a structure for this kind of an argument. It's not a simple arrow situation. It's not a simple and, right? So that's going to be a weird structure that people can't usually detect. Can we imagine a situation though? Yes, this technique will work. So imagine that pigeons are in some family called Columbidae. Good, imagine that's true. Imagine we're in a world where that's true. That technically is true in our world, but again, doesn't matter. We need to use the premises. Now imagine that doves are in this family Columbidae as well. Imagine we live in a world where doves are in that family. Can we imagine that the pigeons and doves are not in the same family? No. In that world, we just imagine they're in that family Columbidae, so they're in the same family, so it's valid. So, in our step-by-step analysis, this argument is valid. So next step, is it sound? And here you can simply look it up on Google. Yes, those are the family names for doves and pigeons, so this is sound. It is valid and sound, therefore that conclusion is necessarily true. Argument B is a proof. Good. So go to argument D. Be sure you labeled these on your handouts in case you need to practice later. Argument D. All snarfplats are whatsits, all whatsits are really thingamabobs, therefore a snarfplat is a thingamabob. I will stop talking about Ariel and the Little Mermaid, one of the best movies ever. But let's just focus on the argument. Venn diagram. In this case, a Venn diagram works. Here we go. Premise 1, all snarfplats are whatsits. So what do you need? You need a larger set of whatsits, and then snarfplats go inside. We'll treat snarfplats as a category, so it gets a bubble as well. So we have a bubble inside a bubble. Then, all whatsits are really thingamabobs. So notice, I hope I can pull this off with my graphics, right? We need a larger bubble for thingamabobs that is on the outside of whatsits and snarfplats. Based on our image, based on our diagram, does it follow necessarily that a snarfplat is a thingamabob? Yes, it does. The argument is valid. Here is a case where structure works as well. Here's our structure. Premise 1, if snarfplats, then whatsits. Premise 2, if whatsits, then thingamabobs. Conclusion, if snarfplat, then thingamabob. Yes, a very common structure. We see this a lot. Transitive property in math. In logic, I think modus tollens, right? There's even a Latin name for it because it's such a common structure. So what do we have? Venn diagram follows, it's valid. Structure, basic structure, has good logic, valid so far. Imagine a situation? No. right? I don't think we can imagine Snarflats or Wutzits, or if we do, I'm just going to start thinking about the Little Mermaid, but that's clearly not what is implied here. We're not sure what these things are, so we can't imagine them. But the first two methods did show it's valid, so answer valid. Is it sound? Are these premises actually true? These premises mean nothing. We can't even understand them. If we applied some imaginary world like the Little Mermaid, great movie, then is it true? No, this is either nonsense or just not true, so we stop. It's valid, but it's unsound. The argument fails. It is not a proof. We stop there. Unsound. Argument stinks. Argument G. Whew, let's see. Does this work in a Venn diagram? Sadly, yes, it does. Premise 1, my teacher is a tree frog. So we create a bubble for the set of tree frogs, and there's your teacher. Premise 2, tree frogs have sticky feet. What do we need? A larger set that fits the tree frogs inside it, that is the set of things with sticky feet. Does it follow that your teacher has sticky feet? Notice, no matter how crazy it is, we're basing it on the logic, not actual truth, but the logic. So we hypothesize or assume that it's true. Does this follow? Yes, it does follow. According to our diagram, your teacher has sticky feet. Apply structure. Let's see if that works as well. Yes, simple structure. If you're my teacher, then you're a tree frog. If you're a tree frog, then you have sticky feet. Therefore, if you're my teacher, you have sticky feet. Again, a very familiar structure, a common, logical, valid structure. So it's valid. Imagine. Here is a case where all three methods actually work if you are disciplined enough to use the imagine a situation method. I am not disciplined enough. My imagination gets away from me all the time. Let me show you my imagination at work. Let's imagine we live in a world where your teacher is a tree frog. Ooh, that is fun to imagine. Tree frogs are adorable. Now imagine that tree frogs have sticky feet. So imagine you live in a world where both of those things are true. Does it follow, or, example, can you imagine that your teacher doesn't have sticky feet? We're trying to imagine an invalid case. Now, if you are disciplined, you would say, oh yeah, I can't imagine that, right? If that world is true, then my teacher has to have sticky feet, the argument's valid. But I can't do this, because what am I doing? I'm imagining my teacher's a tree frog and the tree frogs normally have sticky feet, but then I'm imagining that my teacher was in the Great Froggy Civil War of 1989, and so he's missing his feet. He walks around on prosthetics. He's in the Special Olympics and did very well, by the way. Okay, do you see what's happening? My imagination is getting away from me. I am not sticking to the situation, so I shouldn't use this method, but technically it does work. All three cases apply. We can use all three methods. This is a valid argument logically. So, valid, yes. Is it sound? No. Sadly, your teacher is not a tree frog. Premise 1 is false, so it is unsound. The argument fails. Phew. Argument H. All boy bands suck. Britney Spears is not a boy band, therefore Britney Spears does not suck. Unfortunately, we can do a Venn diagram here. This is the last time I will do this, though. These are awful, and in fact, they don't work for the cases that are going to follow on page 10, so I wouldn't be using them anyway, but this is the last time I will do this. Here we go. Premise 1. All boy bands suck. So we create a set of things that suck, right? I can imagine that would be a huge set, but I only have so much room. Now we put boy bands where? Inside the set of things that sucketh, right? There are boy bands. In the real world, they would take up a lot more space than that, but it's just a picture. So there we have the first premise. Premise 2. Here is where Venn diagrams show their nasty cores, right? They stink. Where do we put Britney Spears if we know that she's not a boy band? Now, clearly, she doesn't go in the boy band circle, but where does she go? According to the premises, we're not sure if she sucks or not. She might be in the suck circle or she might be outside of it. All we know is that she's not a boy band. So, right, where do we put her? Unclear. Now notice, a valid argument must necessarily follow. It has to be true if the premises are true. So, does it follow from our Venn diagram that Britney Spears does not suck? No, we're not sure if she sucks or not. We only know she's not a boy band, but we're not sure if she sucks. So, it's not valid. This doesn't clearly follow. Does it work as a structure? No. Because of the negation, the structure isn't clear for most people. Most people can't handle a structure that contains a negative term. Can we do the imagine a situation method? Yes. Again, this is a good method for us intellectually to understand validity, so let's try it. Imagine we live in a world where all boy bands suck. I am so sorry, Justin Timberlake fans, that guy is cool, but we have to imagine we live in a world that's actually our world. Imagine you live in a world where all boy bands suck. All right, let's imagine that. And then let's imagine we live in a world where Britney Spears is not a boy band. Easy to imagine because that's our world. Does it follow that she might still suck? Notice, we're looking for an invalid case. So can it still be the case that Britney Spears sucks? Yes, that's our world. You can suck for non-boy band reasons. So again, this is not valid, and we stop. We stop because it's invalid. The argument's a total failure. Please, no more Venn diagrams. Let's turn to page 10 and try those examples. Example I. If Doug is drunk again, then he will be stumbling around campus. Doug is stumbling around campus, therefore Doug is drunk again. Venn diagram, no, we're not going to do it again, but we can use the structure. If Doug is drunk again, he will be stumbling around campus. If D, therefore stumbling, S. Premise 2, Doug is stumbling around, so S is true. Does it follow? Conclusion, D is true? No. If you look at it, that doesn't follow from the first premise. If D leads to S, we don't know what follows from S, right? So we have the causal direction backwards, so this is invalid. Now imagine a situation. This works really well. Imagine a world where if Doug is drunk, he'll be stumbling around. So as long as we imagine when he gets drunk, he gets really drunk, then pretty easy to imagine. Now imagine that Doug is over there and there he is stumbling around, right? Does it follow that Doug is drunk, or can we imagine that premises 1 and 2 are true and he's not drunk? Yes, easy. Maybe Doug has a sprained ankle, so he's stumbling around. Maybe he has vertigo. Maybe he has narcolepsy. Maybe the ground's really slippery. We can imagine all sorts of situations where the premises are true and Doug isn't drunk. So this case is invalid. We stop right there. The argument's a failure. Example J. Again, Venn diagram won't work, both because I protest, I hate doing those things, they are not reliable, and also the first premise is too hard to do in a Venn diagram because it contains an or. So let's look at structure. Again, nope, an or is too tricky for us to see a simple structure, so we use the imagine a situation, and again, this one works pretty well. I just have to be disciplined with my imagination. It's either raining today or it is not. Let's imagine that's true. Pretty easy to imagine, rain or not rain. Premise 2, if it's raining, the grass is wet. Again, easy to imagine if it's raining, the grass would get wet, at least eventually. The grass in front of the building MJG is wet, right? So let's imagine, right, that that's wet. Does it necessarily follow that it's raining, or can we imagine it's not raining? Sure, right? I'm sorry. What can we imagine, right? Could be sprinklers, could be a bunch of overhydrated dogs, could be that Doug and all his friends were drunk and so that's vomit on the ground, right? It looks like they drank whiskey, so it's actually pretty clear vomit. Fine. We can imagine plenty of reasons where it's not raining and yet the premises are true. So what's wrong? Invalid. The argument fails. Now, if you look at it, if you look at premises 2 and 3 by themselves, some of you can see that the structure is backwards. We have a similar sort of structure as we just had in argument I, so it doesn't follow. Deductive argument L. Let's look at that, right? All NASCAR fans either have mullet haircuts or wear tank tops. Jethro is a NASCAR fan and doesn't wear tank tops, therefore Jethro has a mullet haircut. Again, structure is too tricky because it's an either or. We can't see the structure. I am not doing a Venn diagram for an either or, so sorry, we ruled that out. Imagine. Now, this can be done. It's a little tricky, but let's see how it works. Let's imagine that all NASCAR fans either have mullets or wear tank tops. So imagine, if you're a NASCAR fan, you either have to have the hockey hair, right, business in the front, party in the back, the number 7, sorry, right, too many words for it, or you have to wear a tank top. All right, so let's imagine that that's a rule for NASCAR fans. Now, we have a NASCAR fan and he doesn't wear a tank top. Well, does it follow that he has a mullet, or can we imagine that he wouldn't have a mullet? Well, technically, if you're disciplined, right, we can imagine him not having a mullet because that's the rule in premise 1. So this thing is actually valid. Now, it's valid. Is it sound? No. Premise 1 isn't literally true. Not all NASCAR fans have mullets or wear tank tops. I know a NASCAR fan that doesn't have either of them. So even just one instance proves that premise 1 is not true. It's not sound. It fails. Example M. A hotshot architect would not have 6 kids sharing one bathroom. Mr. Brady had 6 kids sharing one bathroom. Therefore, Mr. Brady was not a hotshot architect. A structure is also too tricky because it has a negation in it. That not makes it too unclear as a structure. Imagine a situation, though. Can be done, but you have to be disciplined. Let's imagine we live in a world where if you're a hotshot architect, you would not have 6 kids sharing one bathroom. Now imagine that Mr. Brady has 6 kids sharing one bathroom. Technically, we can't imagine him still being a hotshot architect. Hard to imagine, but it is a valid case. He can't be a hotshot architect in that world. So this thing is valid. Is it sound? No. Premise 1, we have no idea what a hotshot architect would do. A hotshot architect could have no bathrooms for all we know. So premise 1 isn't clearly true. So again, unsound. Valid, yes, but unsound, so the argument fails. Argument O, sorry, this is too long for any of our methods. Yes, the structure could work, but it's a very complicated structure. Imagine a situation could work. It's just hard to imagine that some of you can do it, right? Let's finish this because I think you're getting convinced, aren't you by now, that these methods get way too difficult when arguments are tricky and you have to know exactly when to use them. Oh, wait. No. Let's try argument P, right? Great. If you are standing in front of class, then you are the most handsome and intelligent man in the world. Jeff is standing in front of the class, therefore Jeff is the most handsome and intelligent man in the world. So normally on a normal day we would be in class and there I'd be standing, so let's put it into that case. Venn diagram, I'm not going to do it, right? Sorry, you can do it, but I'm not. Structure, here we go. If standing in front of class, then handsome and intelligent. If S, then H and I. S is true. Premise 2, therefore H and I follows. Valid. Imagine a situation. If you're standing in front of class, let's just imagine that we live in a world where if you're standing in front of the class, then you are the most handsome and intelligent man in the world. And let's imagine that Jeff is standing in front of the class. There he is. Look at him in your imagination. Oh, that's brilliant. Does it follow, could it follow that he is not the most handsome and intelligent man in the world? No. We imagine premise 1, we imagine premise 2. The conclusion has to follow. So what did we find in both methods? Yes, we found that this is a valid argument. It is absolutely proven beyond a shadow of a doubt that Jeff, I am the most handsome and intelligent man in the world. What? Damn it. Damn you. Okay, yes, it's valid. Does that mean it's a proof? No, we forgot to ask the second question. Is it sound? Is this sound? No. Premise 1 isn't true. That is not a definition. Standing in front of the class doesn't make you the most handsome and intelligent man in the world. Premise 1 is false. Total coincidence in this case, but it's technically false, so this is not a proof. Sadly, it's valid, but not sound. You big punks, this doesn't prove that I'm the most handsome and intelligent man in the world. This is an unsound argument. So, do you want to use those methods on our next big quiz? Do we want this to be a chaotic free-for-all as you try to draw bubbles, try to prove that you imagine the situation with a disciplined heart? No, we don't want to use those. So, what do you say? Please, Jeff, teach us a better method. Great. Now you are all motivated to learn a much better technique, the technique of symbolic logic, in this case, SL, technically sentential logic. Good. We're ready.